Welcome to Homework Lib.
Hi, so this problem asks us to prepare a buffer solution that has a pH that is equal to 4.3, and we want to mix, for this question, solutions corresponding to 1 molar acetic acid. I'm going to abbreviate acetic acid as HAC, mixing it up with 1 molar NaOH. We want to now get a final volume that is equal to 1 liter of solution, and we know that the initial portion that I'm going to have available of acetic acid, it is going to be equal to 300 milliliters. Okay? So now, one thing that we need to check up before we do any calculation is the Henderson-Hasselbalch equation. So this equation tells us that the pH is equal to the pKa, and by the way, the pKa for acetic acid for this reaction is equal to 4.76. So the pH is equal to pKa plus the logarithm of the concentration of the conjugate base, that is the acetate ion that I'm going to abbreviate as AC minus, divided by the concentration of acetic acid. Now, what happens if I re-express this coefficient, AC minus divided by concentration of HAC, of acetic acid? I can rewrite it as amount of mole of AC minus divided by the total volume of my solution. And the concentration of acetic acid, I can abbreviate it as amount of mole of acetic acid divided by the total volume of solution. So you can realize that the volumes are going to cancel out. So my Henderson-Hasselbalch equation, I can rewrite it as well as amount of mole of AC minus divided by amount of mole of acetic acid. Perfect. So, if I can mix up to 300 milliliters, well, I might as well just calculate the amount of mole of acetic acid that I have in that volume, and that is going to be 1 molar times 0.3 liters. Remember that the definition for molarity is amount of mole divided by volume in liters, so amount of mole would be molarity times the volume in liters. So I have exactly 0.3 moles of acetic acid in my solution. Thus, the only thing that I want to know is the amount of mole of AC minus that I need to add. The way to do it is, well, using this equation. First step, we're going to replace the value for pH, 4.3. Whoops, that really looks awful. Let me redraw it. 4.3 is equal to pKa, 4.76, plus the logarithm of amount of mole of acetate that is going to be generated divided by the amount of mole of acetic acid. The amount of mole of acetic acid is going to be 0.3. So we need to solve for acetate. Rearranging this equation, 4.3 minus 4.76, it is going to give us minus 0.46, right? So minus 0.46 is going to be equal to the logarithm of n AC minus divided by 0.3. We can rearrange this further, exponentiate using 10 as a basis, so that we get rid of the logarithm. So 10 to the minus 0.46 is equal to amount of AC minus divided by 0.3. And with this, finally, we get the result that the amount of mole of acetate that we need to generate is going to be equal to the multiplication of both of these numbers. 10 to the minus 0.46 times 0.3. But wait, now we get an interesting problem because we want to prepare this solution by mixing up acetic acid with sodium hydroxide. I don't have the acetic acid on its own and the acetate ion on its own. But the only thing that is going to change, as you will see, will be the factor of the amount of mole of acetic acid that we have. In order to verify where that change comes from, we're going to take a reaction that is going to generate acetate plus water. In this case, I can completely neglect the sodium plus ion and we can just write down NaOH as OH minus because that is what is actually reacting, right? So we are going to do our ice table in terms of moles, not in terms of concentration. So initially of acetic acid, I have 0.3. Then I'm going to add an X amount of OH minus. And initially I have 0 of AC minus, and water, it doesn't matter because it doesn't enter into any equilibrium calculation. So the amount of change, assuming that OH minus is going to be the limiting reagent, because we need to have some portion of acetic acid in order to keep our buffer. So we're going to have minus X, and X. So amount of acetic acid will be 0.3 minus X, 0, and X. Oh, guess what? We can replace the amount of mole of acetic acid with the value that we found in our equation. So this is now going to be equal to X. And instead of writing down 0.3, this will be 0.3 minus X. Replacing the same thing on the further equations. And over here as well. It turns out that the only thing that I need to do is solve for X directly. And that X amount is equal to the amount of mole of acetate that I'm going to have, and is also equal to the amount of OH minus that I need to add into my solution. So we can proceed from this part of my equation. So 0.3 minus X multiplied by 10 to the minus 0.46 is equal to X. So we have 0.3 times 10 to the minus 0.46. Putting all of the x's on the same side, we have x times 1 plus 10 to the minus 0.46. Solving for x gives us 0.3 times 10 to the minus 0.46 divided by 1 plus 10 to the minus 0.46. The result for x is going to be equal to 0.07724 mole that we need to add. And that X is the amount of mole of OH minus that we need to add. Are required. And now the only thing that we have left is we know the concentration for my acetic acid. This is a 1 molar concentration. And remember, again, this is equal to amount of mole divided by volume. In this case, we want the volume. So the volume of NaOH that we need to add is equal to the amount of mole that we require, in this case 0.07724 mole, divided by my concentration, that is 1 molar or 1 mole per liter. So the result stays the same, or we can express it as the same thing in milliliters, right? So this is 0.07724 liters, which is equal to 77.24 milliliters of NaOH. And that is the final amount that we need to add into our solution. So that is all. Essentially, what we did was just rewriting our Henderson-Hasselbalch equation, write it down in terms of amount of mole. Then we took advantage of the ice table to rearrange these values further, replace the values for the amount of mole of acetate and acetic acid with the values at equilibrium that are x and zero point 0.3 minus x. Solve for x, and that x is turns out to be the same as the amount that we need to add of OH minus for the reaction to happen. Solving for everything, converting the moles into milliliters using the concentration, and that gave us our final result. And that is all. Thank you very much.